everyone. So thank you for being here today. So today we are pleased to welcome Dr. Justin Zhou, a very special guest from University of South California. So Justin Zhou earned his PhD at University of South California, where he was advised by Jonathan May. And his research focused on building human-centric AI by maximizing shared contextual understanding between humans and AI systems. So prior to USC, so he worked at ISI as a program analyst and earned his bachelor degree in computer science at HKU. So he had previously interned at Meta and Amazon AGI, and he led the first team from USC to compete in the Amazon Prize Social Bot Grand Challenge. Wow, and then made it to the semifinals. He also organized the conversational AI workshop at ICM in 2023. Yeah, that's also quite hard, the making and the organizing and then maintaining the managing the AI workshops in the conference. Actually today, so then he will be sharing with us his expert opinion that the title itself is Context Synchronization for Human-centric AI. So let's welcome to the speaker.
Thank you so much for the kind words. I'll jump right into it. Before I get started, I just want to confirm, is the talk expected to be about 1 hour long? Is that right?
That's correct, no problem. Yeah.
Okay, perfect. All right. Great. I don't mind people asking me questions throughout the talk. So if you have any questions, please raise your hand and I'll make sure to channel those through and answer them on the spot as much as possible. If they're going to be longer discussion questions, I'll try to defer them based on the time that I have. But anyways, thank you. Jin Park, thank you so much, Professor Jin Park, for such kind words to introduce me and invite me to this talk. It's a pleasure to be here to be talking about context synchronization for human-centric AI as my dissertation topic. I actually presented this yesterday for my thesis defense, and so it is very fresh on my mind, and I'm glad to spread the word on the vision that I have here to a broader audience. So let me get right into it. Before I sort of dive deep into my research, I first want to define what intelligence is because we're interested in building artificial intelligence. And a definition that I really like from Chris Manning at Stanford is that intelligence is the ability to learn and perform techniques to achieve goals appropriate to the context in an uncertain, ever-varying world. And here, the key term I feel like is context. And which means the interrelated conditions in which something exists or occurs. And as human beings, we make a lot of intelligent decisions. For instance, this is my son, Jude, and when he's asleep, my wife might say something like, Jude's awake. And at 12 p.m., when she tells me this and walks up and, is going to go get him, this is merely a status update. No action is needed. But if this happens at 3 a.m. while she's like, with a frustrated voice tapping me on the shoulder, then this means get Jude, soothe him, and put him back to sleep. And so in this context, I was able to establish her nonverbal communication of like her frustrated voice, even though the semantic meaning of the word Jude's awake was the same in both cases. Both of these situations and interpreting the situation made me take very two different actions. So what about AI? In the simplest case of an example where someone says, is drinking coffee healthy? ChatGPT, the latest version, might give you something like this, very comprehensive, super long, talks about all the different benefits. And in a textual interface, this isn't really problematic because you can skim through it and just pay attention to the parts that matter for you. But what if this was actually delivered through you by voice? It was a voice-based interaction. I don't know about you, but I don't have the patience to listen to all of this, or the attention bandwidth to digest all of it and understand it. And so in a speech-based scenario, you'd probably not want something very long. You probably don't want any of these like speech-based artifacts of like bullets or colons and parentheses. And so there's a lot of like, different behavior that we really want. And so in this case, you can say that the model is not contextualized through the mode of communication. What about the other instance where I have some personal information, like I have hypertension, like a medical condition, and maybe some preferences about wanting to see scientific evidence with any kind of information that's given to me? And what if, I always drink coffee with sugar and cream? That should sort of contextualize the model's outputs, but you're still going to get some generic recommendations about coffee. And so in this sense, you can say that the model is not contextualized to the specific user. Here's another example. Let's say I'm in therapy and I have trouble like building relationships with people, and I tell the therapist that I don't have close friends because I don't trust people. ChatGPT, left to its own defenses, It will say something like, I understand that feeling, building trust with others can be challenging, and be directly empathetic. But in reality, what we actually want from a therapist is to sort of understand the crux of the problem better before jumping into giving some kind of shared understanding. So saying something instead to say, do you mean you don't trust family or people in general? To understand the scope of this person's problem is actually needed to take a more in-depth conversation. Otherwise, it feels like the response, the empathy that you showed before that feels very shallow and ungrounded. And so in this case, you can say that the model is not contextualized to the higher level objective of how to perform therapy correctly. And so hopefully with these examples, I've shown you that utility is a function of shared context. When humans and AI don't share context, the communication between the two is highly likely to be unsuccessful. And so the more shared context you have, the more useful an AI response will be. Identifying the how, like how are we communicating right now? Why are we talking about this? And who am I talking to? And the when and where and when is this taking place is all very important factors for communication to be successful. This kind of lack of contextualization is actually not surprising when you think about the current paradigm of how we train these models. We have this hyper focus on scale and collecting instruction preference data, large amounts, and then there's a lot of pressure for rapid progress because there's high stakes, economic high stakes involved with these big tech companies all competing one another to release like the biggest models and the best models. And this kind of pressure leads to looking for data that's highly available or convenient to collect. And usually, available data is usually textual data. So we have a lot of bias for textual data with the models that we train with. There's a lot of transactional instruction data, as in like interactions are mostly simplified, reduced into a single turn interaction. And then also preference data is difficult to collect a lot of contextualized preference data. So we often just ask, do you like A or B over the another, without really considering maybe all the different kind of scenarios for which one might be actually preferred over another. And then we rely on verifiable evaluations to quickly evaluate models with different ways and measure progress. And this leads to models that lack an understanding for other modes of communication beyond text. This also leads to models that lack personalization in general. And this also leads to models that aren't aware of higher level objectives that go beyond the simple single turn and verifiable sort of domains. So my vision here is to push for context synchronization, which is the shared building more shared contextual understanding between human and AI that is required for fulfilling the human's intended goals. And the research statement is basically pushing for context synchronization. And this talk will take part in three parts. First is macro context synchronization. And what I mean by this is trying to answer the research question of can we contextualize language models to generally desirable behavior that's not represented in large scale training data? And then the next scope is micro context synchronization. Can we contextualize language models to specific desirable behavior under limited data constraints? And lastly, both of these actually have a contextualized data bottleneck problem. So we're thinking about leveraging context simulation. Can we contextualize language models with simulations? So these are the three parts that I'm going to walk through. I'm going to dive right into the first part. The first research question, can we contextualize language models to generally desirable behavior not represented in large-scale training data? And the paper, the represented work that I'll talk about is the speech-worthy instruction to language models from ENMP 2024. So going back to the example that I first showed about is drinking coffee healthy, this, response is totally fine in a textual interface. Users actually say so. The amount of information, the length of the response, and how easy it is to understand were rated all highly on a scale from 0 to 2. But if this response was actually presented in voice, where they were forced to listen to the response rather than read it, the metrics all dropped significantly. The amount of information, the length, and whether it was easy to understand, people tend to find it more difficult. And so you can say that the models are not synchronized in the speech domain. So how do we synchronize language models for a domain that isn't captured in this textual data that we collect? The first method, probably most data efficient and easy, based on your opinion about prompt engineering, is to do prompting. You can distill expert knowledge. You can collect recommendations from the radio industry or the listenability literature on how to compose content that gets transmitted via voice rather than text. And there's a whole array of like different recommendations in that space. So you can condense this and say something like, here, you're a voice assistant now, respond colloquially, be concise without missing key information and use simple sentence structures and so on. So that's great, but that's a great starting point. But when you look into this prompt, you might realize that certain commands here are actually kind of vague. Like, what do you mean to be responding colloquially? Or what is the level of conciseness that you need without missing key information? Or what is really a simple sentence structure? And so these are all just recommendations from the literature, but does not directly pertain to a human AI interaction setting. And so we'll be interested in actually verifying or more specifying these different kind of commands with a data-driven approach. And this is where the second method comes in, where we use reinforcement learning with human feedback, collecting preference data set that is directly capturing speech-based preferences to take a data-driven contextualization approach. And so the key idea here is here we're gonna now have a bunch of textual preference data where people listen to two responses and choose which one they like more. To do so, the first step is to process data where we take a bunch of instruction data that's already out there, but we need to filter out prompts that does not actually pertain well to the speech-based domain. I don't know about you, but I'm not going to be asking with a voice-based assistant to like ChatGPT saying, write a scene between two actors discussing movie Inception. That's not something I'll probably ask in a speech-based domain. Maybe something more just factual, or maybe something brainstorming or asking for quick advice is more relevant for the speech domain. So we filter those out. And the key idea here for pushing models towards a voice-based scenario is to sample diverse responses that might capture what actually users want. But the crucial part here is that we don't want to be prescriptive of the kind of behavior that we want. The whole hypothesis is that we don't actually know what users want in a speech-based domain, and we want to capture that as much as possible. If you naively just make a model, generate a bunch of different responses using, let's say, hyperparameter tweaks with temperature, you will get some different responses, but not differing enough that it might not capture any meaningful signal. So what we do here is we set up different prompts with different granularity. The most simple one is you are a helpful voice assistant, and then the most detailed one, which we use for the prompting technique, and we have 4 or 5 different prompts that span this kind of level of granularity. And we push this through the model, pair different kind of language models to ensure even more diversity, and then pair these responses together for preference data collection. And so after pairing, you put them through a text-to-speech module, and people will listen to them and then pick which one they like more. This way, we've collected 20,000 different preference pairs that directly capture speech-based preferences. And once you have that, we can use the same tools that we use for textual preference optimization, such as DPO, direct preference optimization, or PPO, proximal policy optimization. In the results that I'll show you, all the results will be actually for DPO because the results actually for DPO and PPO are quite similar. So with DPO, compared to the base model that was not fine-tuned at all, we can see that it leads to significant improvements for the speech-based domain because we now have a win or tie rate, 72% compared to the base model. Interestingly, once we just use prompting, we actually get the same win and tie rate, but actually a higher win rate. So one could wonder, was all that data contextualization method worth it or not? Because prompting is much like easier to do. But when you think about it, these two methods actually are not orthogonal to one another. You can combine them, and so that's what we do. And in this case, we combine them, and the performance that we get is, blowing out the other baselines out of the water. We get 86% win and tie rate with the highest win rate as well with 72%. And we further verify that this improvement is actually, in fact, better than the prompt, just only the prompting-based method by comparing DPO plus prompt with prompt. And we get a 51% win rate and 68% win and tie rate. So what accounts for the improvements that we get from data contextualization compared to just using prompting? Well, first we find out by categorizing some of the key examples where DPO plus prompt outperforms prompt, we categorize these into different patterns. And we find that this actually leads to better follow-up questions and being more colloquial, generating more concise responses, and also generating content that contains fewer non-verbalizable content like lists or parentheses and that sort. And so when you look back into the prompt that we had before, the commands of being responding colloquially, being concise without missing key information, has all been specified further with this data contextualization approach. We apply our technique, the prompting technique, to larger models as well. And you can see that for larger models, actually prompting is even better, getting an 88% win rate or win and tie rate compared to the base model. So But then comparing to our best performing model, how does that perform? And so the model that we were using so far was actually Falcon, 7 billion parameter. Like right now, it's very probably outdated. Don't ask me why I used Falcon, and had a lot of like issues with Amazon not letting me use the latest models and all that. But anyways, so GPT-4 plus prompt compared to our best performing model, GPT-4 plus prompt actually comes out on top. But you can see that given the model size difference, we don't know what the model size for GPT-4 is, but Falcon being only 7 billion parameters, being fine-tuned this way actually has a pretty comparable performance compared to this very big model. And when you consider some practical constraints in speech where latency is super important, you want smaller models to be able to generate responses quickly. So to understand why, but what falls short with our contextual data contextualization approach? What makes the small model not as good as the bigger model? What we find out, well, is that when you use DPO and our speech preference data set, reward hacking occurs. And one very frequent pattern that we see is that Falcon plus DPO plus prompt actually leads to overly concise responses. So in this case, the question is Spain a good place to live? The answer is Spain is a wonderful place to live. Would you like to know more about it? So it technically answers the question, but it's not really answering the question, right? It's sensible, but you would actually want a bit more information. And so in this case, even though the GPT-4 plus prompt gave you a much more comprehensive answer, in this case, the longer answer was actually preferred. So it's never just a simple answer of shorter being better just because it's speech. So the takeaways from this first part is answering this research question: Can we contextualize language models to generally desirable behavior not represented in large-scale training data? And the answer is a resounding yes. You can use prompting with expert knowledge for an effective data efficient strategy. But on top of that, you can take data-driven contextualization to improve consistency. So the main idea here is that you can consider multiple strategies for most consistent context synchronization. Future directions with this line of work is balancing speech suitability reward model, potentially with language model as a judge, scores on, let's say, some more basic metrics like answer completeness to prevent reward hacking could be one direction. And the work that we've worked on right now is the text model performing, functioning as a just part of the modular pipeline of ASR, automatic speech recognition, to response generation and to text to speech. So you could try to incorporate this directly into end-to-end speech models. So that was the first part. We went from text to speech, which was very broad contextualization. But what about something more granular, contextualizing to a single user's preference? And this is where we get to the research question: Can we contextualize language models to specific desirable behavior under limited data constraints? And for this part, I'll be talking about tuning-free personalized alignment, which was published to NACL 2025 this year. So here's a different example where now a student is given a task to write an essay about privacy. If we put this naively through a language model, this is the kind of response I will get. Something very generic with formal, structured language saying, for instance, moreover, to address your query. And then it also has like flowery adjectives, crucial, relevant, and significant, which are kind of vapid words that doesn't really mean anything. And if you look at real student essays, they would be a lot more colorful. They would contain all caps or rhetorical questions or even short, assertive sentences to really put their opinions out there. And so ideally, we want these models, when we ask them to, help us with writing tasks, to employ some of these personal style into that text. The challenge with this kind of personalization is that there's usually not a lot of per user data. Each user does not want to give you, does not want to, spend a lot of effort in giving you data. And also they might have privacy concerns, so they don't want to share it so much. And so realistic data setting here is a very low resource setting where there's probably less than 10 samples per user. And we can't make any assumptions about whether we have data from other users that we can leverage as well. We're just going to focus, we're going to assume that, take the most conservative setting that we only have access to this single user's data, and that's less than 10 samples. So in this scenario, fine-tuning becomes infeasible. So what we've done before with this, with the broad contextualization, macro contextualization is infeasible. The naive, easiest solution here again is sort of prompting, like it's an in-context learning example where you can tell the model, here's some positive examples, the handful that we have, and put it into the in-context learning example and say, hey, try to mimic this as much as possible when you do this new task. And this works to a certain degree. Like you will get this, you will see some of the style of having assertive language, I hold a firm belief, go into the output text, but you can see that in the red, there's things that we weren't able to really take out, like the structural words, like in regards, ultimately, hence. So what can we do here? It's clear that the positive examples are not enough to overcome the bias of the generic style that the models have. And so what if we actually consider these as bad examples and get feedback on them and feed them back into the model? And the key motivation behind this is that we as humans actually learn better from customized feedback on our own mistakes. So look at this woman, showing us how to do a squat. I'll look at that. I'll do my best to mimic that as much as possible. And in my mind, I've done the right job. But in reality, there's probably a lot of different things going wrong. And once you actually get personalized, very customized feedback into what you're actually doing wrong, you might have not even have been paying attention to whether your heels were off the ground or how the angle of your torso. So given this feedback, you're able to go closer into the positive sample better. So we're basically applying this idea to language models as well. Now, we start off with a basic naive in-context learning example where the model generates an output. But now what we're doing here is we take this output and we pass it on to a language model as judge. And the language model as a judge will look at this and say, based on other positive examples, whether it's stylistically consistent or not. And with that, produce an explanation. If the verdict from the judge is that it is not stylistically consistent, it will be considered a negative example, and it will be fed back into the next iteration along with the explanation. And you can iterate this multiple times on some kind of held-up validation set that you measure performance for and repeat as needed. With this augmented in-context learning prompt, which we would call trial error explain ICL, short abbreviated as a TICL, TICL produces outputs that are much better representing of the personal style. It contains rhetorical questions that you can see, and you can see these like short, like insert sentences of privacy, essential yes, that's very stylized. And so that's great. But obviously, I've only shown you qualitative results, so we should go on and try to quantify this better. The way we do this with evaluations is pairwise comparisons using language model as a judge for stylistic similarity. You could have sort of expected that this was where I was going with the tickle pipeline. But what we do here is that language model as a judge, when you use it blindly, naively, then it doesn't actually hit the kind of level of performance that you need to use as an evaluation metric. So we benchmark its performance with human data from these two personal writing data sets. The setting here is that the language model is given some candidate beat list, one candidate's text, and then two outputs from two different authors. And the model's job is to make sure that it correctly picks out the right author's text as being more stylistically similar. If you do this naively with a single few shot example, you'll get 77% accuracy, which is, not good enough. But then if you add explanations, you can boost performance up to 81%, which is, slightly better, but still below the human performance that you can get. And now you can actually increase the number of examples that you show to this model, and you can reach all the way up to 89.5% accuracy, which is even better than humans. And if since we're most interested in authors that are like stylistically more what do you call it, conspicuous, you want to pick out the top 10 cases, and when you only focus on those, then we get 96.6% accuracy. So in this case, we're just only focused on very stylized users. There might be some writers who aren't very stylized that like write more generically. So to measure performance gains most accurately, we're just going to focus on the top 10 authors. And so the actual evaluation setting after the benchmarking that we do is pairwise comparison compared to the author's text. And so this is a very challenging benchmark because you're trying to beat the author. You can think of this as like an adversarial setting where the model generates an output and the language model as a judge has to sort of be confused with which one is more similar. And if it actually picks the model's output over the author's own text, then we consider that as a win over the rate, win over the author. And so that is a versus author win rate. The naive solution in context learning gets us a performance around 21%, which is much better than the zero shot performance that we had 2.5. So you can say, maybe this is already good enough. But when you look into Tickle, we actually beat it even further at 31%. Mind you, this is a very challenging benchmark. So like hitting 50% means that you're generating something that's almost like as good as the author all the time and being confused. Hopefully that's the point we'll be able to reach later into the future as these models like develop further. But right now, like even 31%, I would say is quite significant. We also want to look into what actually makes Tickle better than just simple ICL. And for that, we do some lexical analysis to test our hypothesis about, yeah, whether is Tickle actually picking up language from the student better. And so what we use here is a finding words model that looks at outputs from these two different models, consider them as separate distributions, and compare the lexical frequency between different n-grams that appear in these two different set of outputs. And when we do that, we see that unique n-grams to ICL, uniquely frequent n-grams to ICL are more the structural terms that we've seen before. Additionally, therefore, and for Tickle, we see something more opinionated and casual. So why and honestly. So this is one also evidence that shows that Tickle learns more of these casual terms better that is out of distribution from the base model. And also, we verified this even further that the terms that are more uniquely frequent for Tickle are actually, in fact, simpler or in more casual words by using flesh readability ease as a proxy of simplicity of the language that you use. So, flesh readability ease is simply a metric that looks at how difficult a word is for understanding. So, the higher the score, it means the easier to understand. So, you can see here for Tickle, we reached a score of 121 compared to ICL, which is only 36. What makes Tickle work? Well, we first saw that when you add examples and negative examples and their explanations, we see this 10% boost, but we're adding two things at the same time, negative examples and explanations. And there's only one thing we can remove actually, which is the explanations. So, which is the negative examples. Um, Sorry, my robot is actually starting to clean, and I think I'm gonna stop it. Oh, never mind. So here you can see that just adding the explanations, removing the explanations leads to a significant drop in performance, which is only 23.5%. So here you can see that explanations are essential for Tickle to work. Another thing that we need to realize is that model needs to see its own failures. If you actually train a model that is taken with Sonnet, you run Tickle through Sonnet and use that prompt and feed it into GPT-4o, the performance is actually much lower than even just zero-shot GPT-4o. It's at 18.5, not zero-shot, simple ICL GPT-4o. And so models need to see its own failures. If it sees failures from other models, those are out of distribution, though, so they don't really mean anything for these models. But explanations can come from others. So the failures, as long as they come from the same model, but explanations about why they're failures can come from different models. And in this case, Claude 3 actually seems to provide better explanations with regards to style. So the takeaways for the second part of this talk is that we've answered this research question, can we contextualize language models to specific desirable behavior under limited data constraints? And here we say yes. And the reason why we say yes is because we find that dynamic context grounded on the model's own failures is very effective for granular contextualization. And the key strategy for making this work is that we keep on policy failures into the context, and the explanation of the failures are actually very important. Future directions on building on Tickle is improving the Tickle prompt efficiency to reduce length while maintaining personalization signal. You can imagine how the way we've augmented this prompt through multiple iterations can really blow up the input context by a lot. And so being able to manage that into picking out the pieces that actually give the most learning signal, personalization signal, and applying that to the output text is something important if you want to be able to consider more examples or be able to do more iterations to get even more refined kind of signal from the model's own failures. And right now, Tickle is being applied to individual tasks. So if you use it for writing emails, you'll have one Tickle prompt for email. If you use it for writing essays, you'll have one Tickle prompt for writing essays. So ideally, we would want to have some kind of task agnostic personalization prompt that could use a single Tickle setup. So cool. So far, at this point, I just want to make sure we don't have any questions. Doesn't seem like it. I must be doing a great job being very clear. So from macro, we've looked at some very broad contextualization from moving from speech to text. And in micro, we've went from going beyond aggregate preferences into very specific preferences. But in both of these cases, both of these scopes face a contextualized data bottleneck, where we had to think about different ways of creating contextualized data to shape these models' behavior. And so, what if we don't have any contextualized data bottleneck, or what if we want to overcome this bottleneck? And the key idea here is, what if we just create contextualized data from synthetic simulations? And that leads to the next research question on, can we contextualize language models with simulations? And the selected work that I will be presenting for answering this research question is question utility estimation with language model simulations, which is currently under review. So, to sort of contextualize this part of the talk, I want to mention that a question's utility is also very context dependent. So, if someone asks, "Hi, doctor, I'm 35 years old female, I have fatigue and night sweats. What should I do?" So, in this case, the user is seeking for information and like personal recommendations. And in this case, seeking information, the bot should understand that there might be some clarifying questions that it should generate in order to find the relevant information and solution as quickly as possible. So it might follow with something like, "Is anyone in your family sick?" or "What is your temperature?" But if the scenario here now is like a student who's trying to read some kind of learning material and try to improve their understanding of the content, the kind of questions that they ask might be more targeted towards this content itself. So, where is the Amazon? What makes the Amazon rainforest important to the Earth's ecosystem? Might be questions that you want to answer that leads to improved understanding of whatever you're learning. Um, so. Assessing whether a question is useful or not. What is a good question? Defining what is a good question is actually a very challenging task because you can imagine how open-ended this is. For a single piece of content, you can ask millions of different follow-up questions. Maybe not millions, but at least a few hundred different like follow-up questions that are all valid. And which one of these would you say are good, right? And what we're going to say is that good should actually depend on the target task at hand. But prior work actually just relied on indirect measures. So this paper that released talked about salience. Um, Basically what they've done is they've put together linguists that look at the question and analyze it compared to the original content and rate it from a scale of 1 to 5 on how much answering this question would improve the understanding of the text. So this metric is only looking at the question content itself. A different work looked at expected information gain, which is now looking at the answer. So if you answered this question, how much more additional information are you getting compared to the content that you've already had? So now the value of a question is based on the kind of information gain that you will get from answering it. So the problem with both of these approaches is that they're indirect measures. They don't necessarily correlate with the contributions to any specific downstream goal. And a downstream goal in this case might be improved learning outcome. And what we can set up is that a proxy for improved learning outcome could be measured by an exam score. So what if we could directly try to measure a question's contribution at downstream task? An ideal scenario here might be somewhere where a learner looks at a textbook and throughout their learning phase will ask a lot of different clarifying questions that they don't understand, and a teacher might provide answers to those questions. If you are Doctor Strange, or if you believe in a parallel universe and think you can experiment with different pathways and consolidate all those results into one, this is an experiment where you can have the same user, the same learner, basically answer exams with different configurations by looking at only one question without any questions that is asked, or all the questions that is asked, or all the questions minus one targeted question. And then you can have that user take the same exam with these different configurations that will lead to different scores. Let's say got a 30 with one question, got a 10 without any of them, and got a 70 with all of these questions, and 60 with all minus one. And in this case, you can measure the utility or the value of the question as a marginal gain that you get from each of these different questions. Well, this would be impossible in the real world to actually try to optimize for because unless you have a magic wand that erases someone's memory when you wave at a student and make them take the same exam over and over again without all the ethical considerations of even doing that is something that's very not technically feasible. So what we want to do, what we're proposing here though, is that we might be able to simulate something like this using language models. So before we're able to actually go on and simulate this setting with language models, we need a data set that actually has this kind of format where we have a chapter that is paired towards some exam questions that will test the knowledge of that chapter. And so what we've done here is we take the OpenStax repository, which contains college level textbook content, and we put it through a language model that will extract different sections and parse out the questions and create this pairwise data set where we have sections mapped to questions. What we also do just to make sure that we have a data data set that is somewhat diverse. And we classify the exam questions that are being asked for these different kind of subjects according to the Bloom's taxonomy. And the Bloom's taxonomy is a very famous sort of taxonomy in the education space on how to design questions that lead to different kind of cognitive levels that you have to employ to be able to solve them correctly. So lower levels are like remember, understanding is basically just recall, applying, analyze, or evaluate and create our higher level cognitive skills that you need to be able to solve questions. And as you might expect, we have five different subjects here: U.S. history, sociology, economics, chemistry, and microbiology. When we classify these outputs with this Bloom's taxonomy technique, we find out that certain subjects like microbiology, as you can imagine, is probably a little bit more recall oriented. We'll have a lot of remembering and understanding questions. And the same goes for sociology. But for courses like economics, for instance, or chemistry, have more of the applying or analyzing kind of questions. So all this to say that the data set that we collected and processed has a diverse kind of set of questions that it asks. So now with this preliminary sort of setup taken care of, now we want to actually build out the simulator. So here's this like very overwhelming diagram, but I'll work through it step by step. We call it the question utility estimation with simulated tests, abbreviated as QUEST. And what Quest does is basically simulate the setting that I showed you before with the student. The student now reads the document and generates a question. This question generator is like the main component that we're interested on improving. So we're just going to leave that part as is. And the next part is to generate the answers for these different questions. For simulations to be really useful, a key requirement is that these simulations have to be valid. So each individual modular step of that simulation, we validate it as something reliable in order to be able to extract meaningful signal out of these simulations. So the answers get generated, and we test whether these generated answers are correct by, manually picking out 100 of them and testing whether they're actually right, and they turn out to be all correct. These are entry-level college courses, so luckily LLM's theses are very good enough to be able to answer these questions zero shot without any more complex tools. Now, the next component is now we have these questions and answers, right? And we want to see the effect of having these questions on some kind of exam that we're interested in doing well on. And so this learner is going to simulate the setting where it takes on different subsets of these questions and take the exam, which produces some answers from that learner. And so here we're trying to predict the learner's answers to exam problems given these different kind of configurations, and based on that, quantify questions utility by simulating the learner's mental model. This validating this part is actually the core crux of whether this simulation was useful or not. So I'll talk about more of the human evaluation for this later. So once we have the answers from the learner about the exam, we can now have another separate evaluator that looks at the learner's output and the exam question and see whether it's actually correct or not, which is important. Otherwise, the exam scores, if they're not valid, then this whole simulation doesn't work. So what we do here is sample 50 answers from each of these different subjects, and we find out that in most cases, 248 out of 250 were correct. And for even multi-parted complex questions, the evaluator actually does a fascinating job of appropriately giving partial weights. Let's say if the question is a multi-part question and like one of the part of the answer was incorrect, then we'll give like a 0.8, for instance. Next, once we have these evaluators provide the scores for these exams, now we can pass it through the utility estimator with the same setup that we showed before, where it takes on different subsets and produces a score based off of that with the marginal gains. And by that, now each question that we've generated is paired with some kind of score on how it affected the outcome of the learner for the exam. And so based off of that, we can use we filter out for high utility questions, which we set as the top 80th percentile of all the scores that we get. And we use those and fine tune for rejection sampling. So now with the actual results, on textbook exam scores on the held out test set, without any questions and answers, the base model, with its only parametric knowledge, is able to get 24%. And obviously, we gave it the system prompt about, hey, you're a student that you don't know anything about these like exam questions. So that gets you 24%. But with a zero-shot approach where you have a model that's not fine-tuned for any kind of question generation purpose, just saying, hey, generate questions that will improve understanding as much as possible, you will get 44.5%. And if you give it some examples from other past earlier chapters, you'll get 46.4%. With chain of thought, you make the model think a little bit more, give a reasoning before why you produce this question on why it's going to improve your understanding of this content. That leads to a very small amount of improvement. And SFT here is actually a very interesting baseline, which is a model that is directly trained to take the content, the chapter content, and predict exam questions. So what we're trying to do here is sort of cheat in the sense that we're having these models look at the test time content and try to predict exactly what kind of questions that it will be asked on, and then see whether those questions actually hold up as like the same distribution of the real test exams and do well on that. But it turns out that if you take this approach, the model actually seems to overfit to each of the textbook content and leads to even lower performance than zero shot. So, surprise, surprise, this wouldn't be a paper if Quest didn't actually outperform all these baselines. So, with using our simulated approach, we actually outperform all these different wide variety of baselines, with Quest hitting 55.1% average exam score across all textbook subjects that we mentioned before. What's interesting here is that, well, in order to really validate whether utility is a useful metric, is to invalidate the usefulness of other metrics. So what we can do here is basically take the metrics from previous work and do the same thing, rejection sampling, but based on high scores for these other different metrics. So we've shown that using our metric of utility greater than 0.1 gets us 55.1. But if we use like salience greater than 5, that will only get us 49%. If we use EIG, we only get 44.6%. And so these are compared to our quest-based approach, minor improvements on top of the base zero-shot approach. Another interesting thing here is that even if you fine-tune a model specifically for utility, it turns out the questions that you generate with this utility optimized model generates questions that also score highly on other metrics, other indirect metrics like salience. But the opposite wasn't true as you've seen in the previous example. So that's quite interesting. And we try to understand the unique value of utility. And what we've done here is see whether like they have some strong correlations with previous metrics. With salience, there seems to be a very, well, actually no correlation. And EIG, almost a negative correlation. Very small numbers though. You can say it's just not related at all. But what we realize what we can actually compare is utility actually just predicting exam questions better than other metrics. And so this seems to be somewhat true as you can see with the exact exam embedding simulator. You can see you got like a 0.25 correlation, which is much stronger than the others, but still considered kind of small. So it explains the performance partially, but it on its own is not enough. And exam rouge is a different way to check for similarity. But Bloom's taxonomy seems to be also slightly related, like whether you're on a good, whether you predict the Bloom's taxonomy level correctly, does that actually translate to better performance? That seems to be kind of low as well. So all that to say, utility captures a unique learning signal that's not captured by other previous metrics. So this work would not make any sense at all if utility doesn't actually translate into improved learning outcomes for real human beings. So what we do here is a human evaluation setting where we now take the chapter section and they look at three different questions. One question uniquely high utility, one question uniquely high salience, and one question uniquely high in EIG. And they look at these different questions and they're answering a relevant exam question. And what they do after answering the relevant exam questions, they will look back into these questions and rate which ones were most useful and not, from a Likert scale of 1 to 5, and rank these questions accordingly. And so this is the actual human interface that you'll see. With the content on the left side, questions in the middle, and the exam problems on the right. And the survey only pops up after you solve the exam problems. And so here you can see the metric that we're asking for is the level of usefulness from 1 to 5, level of interestingness from 1 to 5, and the rank, where 1 is most preferred. First thing we see is that correlation between the perceived value of usefulness among the human evaluators and the utility metric is the highest at 0.321. And compared to the other metrics, they're much lower, right? There's almost, actually, they're both of them are negative. And so you can say that our utility metric is doing a wonderful job compared to these other metrics in being able to capture this. The caveat here is Compared to social science standards, a zero point 0.3 correlation might still be considered weak to moderate kind of correlation. So there's still definitely room for improvement in terms of using these, improving the fidelity of these simulations to get higher, even higher correlation between utility and human value, human perceived level of usefulness. The other metrics that we've shown before on like the average value of the usefulness and interestingness and the mean rank, we see that utility comes out highest for usefulness, as you probably would have expected from this correlation value. But for interestingness, it doesn't mean that generating useful questions necessarily correlate or regress on interestingness. So interestingness is actually quite similar across the different metrics. And as you can expect, the mean rank is the lowest or the best for utility-based questions. So the takeaways here is that we were answering the research question, can we contextualize language models with simulations? The answer is yes. If you create a simulation that's carefully validated with each of these modular components, the results from that simulation can translate to language models that are more contextualized to the desired outcomes that you've actually simulated. And simulations here is really interesting and promising because it enables studying contexts that are intractable or very difficult to replicate in the real world. Future work for this direction is to think about ways to improving simulation fidelity with better user models. So most of the models that we're building right now are actually assistant models where they're serving as assistants and they're not optimized for mimicking human behavior as much as possible. So once you train models specifically to do user model simulations better, then we might be able to get better performance. And there's been pretty recent work that came out, the user language model from Microsoft, which is specifically optimized for this kind of goal. And so we also want to study some of the theoretical limitations of simulations. We've only worked with a single persona of a user for our simulation setting, but you can imagine how different personas, different learning habits or styles could really lead to different kind of simulation results. And being able to capture this full like diversity of human behavior through these kind of simulations is going to be an interesting future work. So cool. That's sort of how I covered the three main parts of my talk on context synchronization, on building shared contextual understanding between human and AI required for fulfilling humans' intended goals. We went through three parts: macro context synchronization, pushing models towards very generally desired behavior that applies at the population level to a lot of different people; micro context synchronization, something that's very specific to a single user or a single use case; and context simulation to overcome some of the contextualized data bottleneck from the previous two approaches. Next steps for context synchronization. I know my work, it seems like it covered a broad range of things, but there's still a lot of room for improvement. So far, all the work that I talked about actually is limited to verbal dyadic interactions, where most of the interactions are taking place in speech and text. But we should actually be heading towards an omni-model, multi-party context synchronization, where the signals that we can incorporate into these communications become a lot more rich to capture the full spectrum of human communication, where nonverbal communication, where my hand motions here indicate something, or my facial expression express something, and humans all like have a shared sense of smell or tactile senses or understanding of movement that they naturally have a shared understanding. So having these models become more embodied to have the same kind of shared understanding might be useful for even more long tail kind of tasks where these things matter. And as we have more advanced devices that we build AI directly into, being able to manage even like a first person point of view from the human's aspect, like this is something that you don't even see between humans. You don't have another person literally breathing down your neck, looking at the same thing with you at the same time. So this is a very unique kind of setup where you have an assistant that's looking at the same thing as you and being able to understand the context in a first person point of view from individual humans is going to introduce new context synchronization challenges. And also, we said dyadic, but ideally, humans aren't just going to be isolated with one another. Humans are going to continue to collaborate with one another. And in that case, we probably want AI to be able to fit into this scenario, this collaborative setting with multiple humans and maybe a single AI in there, and to be able to manage non-dyadic but multi-party dynamics of interactions that are much richer and probably more diverse and is something that we also need to consider. Also, so far, most of my work has actually been about humans understanding the contextual gaps between human and AI. So we've just been looking at hey, they're not good at speech, so we're going to make them better for speech. They're not personalized, we're going to make them personalized. They're going to need some kind of simulation to be better for a certain task. But there's only so much that the human can identify ahead of time, pre-deployment of a model to bridge these kind of gaps. And so there will be a point where it makes more sense for AI to be actually taking the more proactive role of identifying contextual gaps and bridging it from their end. And so this motivates more proactive and collaborative context synchronization, a complete revamp of how we think how language models or these AI assistants behave. And this is super important in order to go from task-centric to human-centric models. And what we mean by task-centric is what we're seeing right now. Task implicit with any kind of assumptions. We don't know what it is, just a task. And the model works and tries to get to some kind of solution. But this model actually fails when all these implicit assumptions are not aligned at test time. And so this is what I believe to contribute most to misaligned systems. And instead, what we wanted to do is something like this, where we have a human-centric system, where the human has this rich context that the model understands. And even in that case, sometimes what gets verbalized might not be enough, so that the AI actually tries to clarify things and bridge the context further and takes a more interactive approach to some kind of intended outcome, where the intended is the key term here, where the outcome is something that the original human actually wanted. And this is important. I feel like a super important direction that I would want a lot more people to be working on because it's this task-centric setup of AI is leading to a lot of problems for society. They are just one-shotting problems for us. Students are turning out delegating more tasks directly, blindly to them, and from that, they're not using their brains as much. You can see this trade-off between their brain and using AI, and all these articles coming about using AI makes you stupid. And that's not a surprise. If you delegate all your tasks directly without any critical thought on your part, if you're a person who can walk just fine and you go on a wheelchair all the time, your legs are obviously not going to be, they're going to atrophy and your legs are probably not going to be good for walking anymore. And the same goes for, thinking. So it's super important that we think more about the human-centric outcome when we utilize AI, the end outcome being more capable humans and more rewarding and fulfilling lives. And one direction in this scope that I'm super passionate about is expanding human capability through models, understanding, becoming better educators or teachers by modeling zone of proximal development. And zone of proximal development is just a fancy term where teaching something that's just just out of reach for you on your own, but with some kind of scaffolding and help, you're able to reach. And humans learn the best when you constantly push yourself into your zone of proximal development through effective teachers. And I think language models have the promise to be able to model these zone of proximal development for individual users and make a very hyper customized learning trajectory for building humans to become more and more capable. And so this is a direction that I'm vouching for a lot, and hopefully a lot more people actually push towards this direction. So that's all for my talk. Thank you. I have this slide for saying thank you to for everyone who've made my journey possible. Definitely was not a solitary effort. I had a bunch of mentors across faculty and industry mentors, both at Amazon and Meta, that have helped me throughout the years, and a lot of talented colleagues at USC and beyond that are all doing amazing things for making all these collaborative efforts possible. So I want to put a shout out to a bunch of my collaborators here. And so I think that's my last slide. Thank you. That's all. I
Yes, thank
realized
you for
there
the
was a lot of things
presentation.
in the chat. Sorry, I
Yeah, there are
completely.
so many questions.